Hi, everybody. Welcome to, I guess this is asynchronous video number 4 for June 2nd, 2020, our summer class. In this vector, we're going to talk about uniform circular motion, which I will often simply use the acronym UCM. So the important word here is circular. So when you think about circles, you think about, well, we think about roundness. In physics, the word circular means something very specific. It means going around in a circular path. In other words, circular corresponds to the kinematics of objects that can be represented as individual points, and their position traces the path of a circle. This is in contrast to things that rotate. Right, so if I rotate, we call that motion in physics rotational. But if I travel along a circular path, my hand moving on a circular path there, then that's called circular motion. And uniform circular motion corresponds to the special case when the motion in a circle, so there's a circle, and just for reference, I'll define the radius of that circle as r. And I'll have a particle moving on the circle, say the particle's right there, for example. And at some instant in time, it will be moving at some particular velocity, and I'll represent the vector corresponding to the direction and the magnitude of the velocity as this little pink arrow going here. And on any path, but a circular path, it's pretty obvious. The vector velocity is tangent to the path of the circle. So it basically goes around, the particle goes around. And if it's uniform, what we mean by uniform is that the magnitude of the velocity vector is equal to v, which is constant. And just for reference, when we have a constant magnitude of a velocity vector, that magnitude vector, whatever we call it, that vector, the magnitude of the vector is called v, is called a speed. And so if the magnitude is constant, then we say that the speed is constant. Now I want to emphasize something. Just because the magnitude of this vector is constant doesn't mean that the vector itself is constant. Indeed, as the particle moves around, say the particle comes over here, say at this point in time, even if the speed is constant, which is to say the magnitude of the velocity vector remains unchanged, this vector is pointing this way, whereas this vector here is pointing that way. So even though the two vectors have the same magnitude, they're not, the v is not a constant vector. V is changing with a function of time. V points this way, and then later it points this way, and then later it points this way. As it moves around the circle, V is constantly changing direction, even though it's maintaining the same magnitude. So since V is not constant, what can we say about the acceleration? Now remember, in one dimension, if v is constant, the derivative of the position as a function of time in one dimension, if v is constant, dv dt is equal to 0. In one dimension, if I have constant speed, if I'm moving in a straight line, the derivative of a constant speed vector in perfectly straight line is 0. But here, something is changing. But what is it that's changing, and how do we figure it out? One way to think about it is, well, we can formally work out what this is, but let's just try it for starters for an intuition. I mean, here's the idea. In this case, the speed is constant, so we're neither speeding up nor slowing down. If we were speeding up, that would correspond to a vector that was pointed in the same direction as the velocity. In other words, if I have an acceleration, a change in the velocity that's in the forward direction, that means I speed up. And if I have a change in direction, this is my velocity vector, this is my acceleration vector. If I have a velocity vector that's pointing in my opposite of my direction, that means I'm slowing down. So this is speeding up, and this is slowing down. In this case, in uniform circular motion, I am neither speeding up nor am I slowing down. So that means that the vector can't point forward and it can't point backwards. And furthermore, if I can break any vector into components, that means there can't be a component that's going forward, and there can't be a component that's going backwards. So what vector is neither parallel forward or neither nor parallel backward. These are disallowed. Any vector that's aligned with the velocity is not allowed. So I need a vector that's not aligned with the velocity. I need a vector that is perpendicular to the velocity. Now, perpendicular does not totally solve the problem, because if this vector points this way, then that vector is perpendicular, and then that vector is perpendicular. Which vector do we want? We want the vector that is perpendicular but pointing towards the center of the circle. So if that's the center of the circle, then I have a vector that's pointing in this direction, and I call that vector acceleration. That is the acceleration for uniform circular motion. So I haven't proven it to you, but I've kind of argued intuitively that there has to be a vector that's basically pointing towards the center of the perpendicular to the velocity vector. And by the way, as this particle moves, any location, the acceleration is basically pointed towards the center of the circle. No matter where I am, that's the direction of the acceleration, towards, that's supposed to be towards the center of the circle, right? So the vector A, which is for uniform circular motion, we will label the vector AC, where this means that the acceleration is centripetal. Centripetal, spelled just like that. And this means centripetal, towards the center of the circle. So anytime I'm moving with uniform circular motion, as soon as I tell you I'm on a circular path with constant speed, you immediately know that the acceleration is towards the center of the circle. That's cool. What else do you know? Well, again, it's a little tricky to prove it without having the tools, but we're going to do it like today, later in the active class. You might want to ask the question, well, what is the magnitude of the centripetal acceleration? Which, again, I will just write as the A sub C without a vector in it. And you can convince yourself that the faster you go, the more acceleration, because it's basically you have to change the vector faster. And the sharper the curve, which is to say the smaller the radius, the more acceleration too. And if you work it out, you can show, and again, we will show it in class, but we haven't done it yet, that the magnitude of the centripetal acceleration is equal to the speed squared divided by the radius of the circle. This is always true. As soon as I have uniform circular motion, as soon as I give you, I'm moving on a circular path with constant speed, you immediately know that the acceleration is towards the center, and you immediately know the acceleration is equal to v squared over r. And by the way, all of these quantities are kinematic, which is to say they only matter, all that matters is the description of the motion, the speed and the radius. And as soon as you got that, you've got the acceleration. So that's it. As soon as I tell you you're moving on a circle, I don't have to tell you anything else except for where I put my eraser. Gonna have to go to my backup eraser. Good thing I had a second one. All right, so this is the most, by the way, this is the most important thing you need to know about uniform circular motion, that the acceleration, that as soon as I'm moving in a circle, the acceleration is centripetal and it has a magnitude v squared over r. There's a few other definitions that are common for uniform circular motion. So let's make sure we got them in our pocket. One of them is something called the period. So the period is how long it takes to go around the circle. Yes? So for example, if I had a particle that took, like our hands of a clock, if I had a particle that took 12 hours to come around the circle from here to here, it would have a period of 12 hours or whatever your favorite thing is. It's not hard to figure out what the period is. There's lots of different, sometimes the textbooks use T. I'm going to use P for period. And the easy way to sort of figure out the period is to just use the fact that the speed is constant. So in other words, the speed is just the distance around the circle, which is 2 pi r, that's the circumference around the circle, divided by the time it takes to get around P. So you can quickly figure out that P is just equal to, well, let's see, I bring the P over here, bring the V back here. So P is basically equal to 2 pi r over V. Yes, that's easy. Okay, and let's check to make sure that the units make sense. So that's 2 times pi, no units. R is length, like meters, and V is like meters per second. And so when you invert meters per second, the meters cancel, you get seconds. Hey, it works out good. So you check the units and you're happy with this and everything looks great. Another term that we often use is something called the frequency. I'm going to put this in quotes because the definition tends to be a little bit somewhat depending on what you're going to do. But the usual way we define the frequency is just equal to the inverse of the period. So basically, this is now periods in time, like seconds, and frequency is in inverse seconds. And it basically corresponds to how, every second, how many rotations does that particle come around. So it's basically in units of rotations. So put rot in parentheses per second. But really, rot is unitless, so it's really per second. One last thing, and we're done. Suppose I'm interested in, suppose I'm looking at uniform circular motion. So redraw it here just to keep track of what we're doing. There's no, well, that's supposed to be a circle, sorry. And the particle's here, and then it moves to here. So the particle has some velocity here and some velocity here. But it basically moves an angle as it changes basically in that location. So in other words, instead of measuring what the linear velocity is, I basically could ask the question, how fast is the angle changing? Obviously, the faster the particle moves, sorry, we're going this way, the faster the particle moves, the faster the rate and change of angle. So we can define something called the angular frequency, or the angular frequency, which is sometimes and equivalently called the angular speed. Either word is fine, angular frequency or angular speed, either one. And it's just the rate of change of the angle. So if the frequency is basically rotations per second, and it takes, well, how long to get around, what angle all the way around? That's 2 pi, at least in radians. So angular frequency, which I will label by the Greek letter omega. This looks like a W with bottom lines. That's not a W, that's in the mega. Okay, omega, well, that's just equal to the frequency, but of course I get 2 pi for rotation, so 2 pi over the period, which is just equal to 2 pi times the frequency. And again, that's in units of radians now, angle, radians per second, which the radians are unitless, so it's really units of radians per second. So that's the definition of omega. And there's only one last thing I want to do, and that is if I've got uniform circular motion, what can I do? So if I have uniform circular motion, then the centripetal acceleration, that's equal to v squared over r. But if I take this relationship, omega is equal to 2 pi f, and I basically substitute in the expression we had right here, which I erased, for p, I can basically demonstrate that the omega is equal to v times r. Okay? So this thing has a name. It's called the rolling constraint. Now, why it's called the rolling constraint, you will see when we get to rolling things. But for now, this just follows from the algebra of everything I just did. So this basically says, you know, the rate of the angular frequency is dependent on the velocity and the radius. So that makes sense. Oh, it doesn't because I've got it backwards. That's what's called writing it down wrong. V equals omega r. That's a little better. All right. I was just had a brain crisscross there. Now let's make sure we've got that right. This is meters per second, and this is meters per second. So yes, we've probably got it right now. So again, this is called the rolling constraint. And once I have this statement in, I can plug that into there, and I get that omega that a sub c is equal to omega squared times r. So if I'm measuring the motion in terms of its linear velocity v, the centripetal acceleration is equal to v squared over r. If I'm measuring the motion of the particle in uniform circular motion, again, this is all uniform circular motion, then the centripetal acceleration is equal to omega squared times r. So you have two ways of calculating the centripetal acceleration, depending on whether you're given the linear or the angular frequency or velocity. All right, that's all for now.